Hello everyone, thanks for coming and for the opportunity to present some of the work. So the talk will be about two papers with my collaborators Yuri Krutov and Shunyu Yao. Shunyu was at Stanford and Yorit's actually at IES now. I forgot to modify that, so sorry Yorit. One paper came out in August and another paper will be coming out, I guess, in a month or two, I don't know. Nope. I'm missing some stuff. Okay, it should be fine. So the goal for today is to understand how the Plateau emerges from the perturbative sum of wormhole geometries in the gravitational path integral. And yeah, we'll mostly be working in 2D Delton gravity because we can make things quite concrete there, and we like that. I'll start with the introduction. I assume you all kind of know what this ramp plateau thing is, but I still like to explain it a bit in the beginning. Then I'll give the main result, which is some new type of universality. And I like to start by giving the results so that you all kind of know what I'm working towards and I'm not wondering half of the talk where this is going. And then I'll just give basically three derivations of this result. The first derivation is kind of the boundary perspective. And then I have two bulk perspectives to give you. One is a Euclidean calculation and one is a Lorencium calculation. Now, the Euclidean one is a bit like, it requires some formulas, so I apologize for that. It may be a bit more technical, but I've tried keeping it to a minimum. The other stuff should be fun anyway, I think. Okay, for some reason it always jumps, but now some intro. As you know, like without properly quantizing gravity, correlation functions that we measure in a black hole background, they eternally decay to arbitrarily small values. It's essentially an incarnation of a cluster decomposition principle. However, when treated properly, like a full system of black holes and the perturbations that we put on it is some finite entropy system, and in such a system, nothing can really decay forever. Like we all know Poincare recurrences. And okay, what happens here is a little more refined version of that, but the idea is kind of the same. Now this tension between what the proper quantum mechanical description of gravity is telling us and what the naive semi-classical description is telling us is kind of a version of the information problem, because we can think of this late uptick in correlation, like instead of decaying forever, it giving some non-zero thing at late times, as basically due to particles that we thought were thrown into the black hole super long ago reappearing near the boundary. Andreas? Yes?
But that would be true for any chaotic system, right?
Sorry?
That would be true for any chaotic system.
Yeah. Oh yeah, true. Though I'm thinking about black holes mostly, I guess. And the idea is that the chaotic system, any chaotic system is maybe in some sense dual to black holes in the bulk or something, I guess. Now, to resolve this confusion, we'll consider an idealized version of the two-point function people have studied for quite some time, known as the spectral form factor. And that's this guy over here. Boom. It's a product of two partition functions, basically. Double sum over eigenvalues. So quite simple. And there's a fun fact that after time averaging this thing a little bit, for generic chaotic quantum systems, one finds a universal late time profile, which is this minimum of e to the entropy and time. And if we Laplace transform this to fixed temperature, that kind of looks like something like this. So we start with some linear, quote-unquote, early time onset All of this is super late time, but I'll call it early time for the purposes of today's talk. And then we have this other curve, which is the exact answer, which starts linearly and ends up at some finite value, which we call the plateau. And this plateau you can think of in this double sum as coming from the terms where EI equals EJ. So we see then, okay, EI equals EJ, we get one sum, 2 beta, gives us Z of 2 beta. Okay, so as I told you, these diagonal terms. Now, of course, this is in a really continuous system, this would not happen, because this would be like taking a measure zero subset of the thing. And in this sense, explaining the plateau using the gravitational path integral is kind of like asking gravity, okay, why are you discrete? Can you show me that you are a discrete system without looking at the boundary description? And that's kind of what's at stake here, I would say. Okay. So how do we compute this guy in gravity? Well, it's going to be a bit of a wild ride here, it looks like. But in gravity, one computes the spectral form factor by path integrating over all geometries with 2 asymptotically ADS boundaries. And these beta plus IT and beta minus IT guys, they feature in the boundary conditions, telling us roughly what the metric is at the cutoff surface, as always in holography. Now, in particular, the types of configurations that we're interested in are like wormhole geometries that connect the 2 asymptotic boundaries. Now, it's been known since 2018 that this linear ramp piece, this early time feature, is explained by a single wormhole connecting the 2 boundaries. So that's nice. It's very universal also. However, the gravitational origin of the plateau has remained much more unclear. And the reason that it's remained unclear is some common lore, which is that it is a non-perturbative effect, and thereby a non-perturbative effect in the number of wormholes, and thereby going beyond any notion one might have of geometry. Well, or what I consider a notion of geometry, at least. However, building on some work by Okayama Sakai and Sat Stanford, Yang and Yao, we found in the papers I'm presenting today that the lore is an artifact of working at fixed energy. And we can understand this a bit because at fixed energy, this ramp plateau structure, minimum of e to the entropy and time, it has some kink. So obviously, if you Taylor expand this for early times, this series is not going to converge. Like non-analytic features, almost by definition, are non-perturbative. But now when we go to fixed temperature, and we smear out this guy like this, then this kink becomes smooth. It's just a nice analytic function. And nice analytic functions, well, also almost by definition, have a Taylor expansion. And that's basically why at fixed temperature we can hope for a perturbative explanation of the plateau, whereas at fixed energy it doesn't happen. The reason people have studied fixed energy in the past and not fixed temperature is because that is what is done in this random matrix literature. So this ramp plateau thing originates from the random matrix literature, and there people always look at fixed energy because that's like a natural basis to work in. But in gravity, I would say that fixing temperature is more natural because it's like fixing a length on the boundary or something. And then, well, we're fortunate that some things are better behaved then.
So the RAM has this saddle, right, at fixed energy, but not at fixed temperature.
Yes.
That was some nice thing about fixed energy. Is there something, like the calculation you're going to do here, is it going to be like a fully integral, or there's a saddle point there?
But there is actually, there is also in some sense a saddle at fixed temperature. But what you need to do is like not enforce all of the equations of motion in some sense. It's a bit like if we have the integral dx e to the minus x from 0 to infinity. This doesn't have a saddle, but it doesn't mean it is still dominated by small x, and also we can still compute it. And the wormhole is a bit like that, where x is the length of the wormhole. So even at fixed temperature, you can still get the wormhole amplitude out of a classical calculation. Maybe I'm actually not answering your question.
No, I guess that's right. Okay, I was just asking, like, the calculation you're going to do now, will it require an integral like that, or it's like a Saturn point?
It will require an integral like that, yes. A fancy version of that. Okay, now to very concretely state the result that we got is like take a generic spectrum, rho of E, with a square root edge, and let's sum over all wormholes in the bulk into the Delton gravity. The sum decomposes in a sum over the number of wormholes in the bulk, like this. And what we found is that from a variety of perspectives, the amplitude with G wormholes always grows as t to the G plus 1. G wormholes, I mean like G extra wormholes on top of the original connected geometry. Maybe I should say G plus 1, but now you know what I mean. And moreover, this sum always converges to the correct Plateau value. And it's mainly this universal feature that genus G wormholes at late times grow as t to the 2G plus 1 that I'm seeking to explain today. Okay, one important aspect here is, and a part of the reason of this convergence is that we will work in a particular late time limit, where time is basically sent to infinity, and this Instanton action is also sent to infinity, but with their ratio fixed. It's like a technical trick that makes life easier. It's the same regime where we can trust this minimum of e to the entropy and time formula. So just so you kind of have a picture in mind, this is one such convergent series. So, okay, the numbers are the genus, and you can see very nicely that, okay, if I just ramp up the genus, this is going to better and better approximate this ramp plateau thing. So the rest of this talk will be about how to find these powers of time. And there will be 3 complementary perspectives, as I said, 1 boundary perspective, and 2 bulk perspectives. The first is kind of boring, but also the easiest by far. So let's do that first. This is the boundary perspective, where we take our random matrix answer, or the answer you get from, say, periodic orbits for quantum chaotic systems. Like, we just take this answer, and we just literally compute the Laplace transform, and then Taylor expand it. So, okay, this is not very hard. If time is fixed, and we have large enough energy, then this minimum will be t over 2 pi, so we have this piece. For all energies bigger than some energy of t, where energy of t is the value where basically t equals 2 pi rho of energy. And then, okay, the other situation for low enough energy, we have this part. This integral can immediately compute. And then we can see that these 2 guys combine nicely like this if we do integration by parts. And in this equation, E of rho is the inverse function of rho of E. Okay, this is a bit stupid, but this guy is very easy to Taylor expand, whereas this guy is not so obvious, at least to me, how to Taylor expand in time. So to proceed, what we need is just the inverse function, energy of rho. The models in which we're interested, rho of E as a small energy expansion starting with the square root and then adding integer powers of that. And okay, then you can use some inversion theorem to prove that this energy is basically an expansion in even powers of rho times e to the minus entropy. And that means that also this, like the exponential of an even function is still an even function, of course. So kind of trivially, we get an expansion of this type with coefficients that are pretty easy to compute given a given spectrum, but I won't bother you with that. At any rate, we can just now compute this integral and get the expansion that I promised you. Now, at this point, I'm just doing a random matrix calculation or a periodic orbits calculation, whatever. But since we know that in Delton gravity, topologies are weighed by e to the other character times entropy, it's highly tempting to identify in this series K with G, the genus of the wormhole. And so this suggests the claim I made in the beginning, namely that the bulk amplitude with G wormholes should grow as time to the 2G plus 1. So, okay, I've said this now I think 15 times, and we'll try to prove this. So the first proof will use Euclidean wormholes, but the mechanism by which these powers will come out is, in my opinion, quite unintuitive. Like it requires like large sums of of rational numbers with very large denominators and denominators to add up to 0. We can prove that this happens based on some math results, but for some reason I don't feel like black holes in the real universe play by that game. But still, I think it's very nice to see it explicitly in 2D gravity. But for that reason, we also worked out Lorencium perspective, where these powers of time have a much more intuitive explanation. However, the detailed calculation is more difficult than in the Euclidean case. And the point is that the powers just arise from counting basically the 2G locations where a baby universe is born or dies. I'll have some pictures for you by the end of the talk. Maybe I should have included one here. And the idea is that those locations should be approximately 0 modes for late times. And I mean, in some sense, this is obvious. Like, even in like all the baby universe papers that people wrote a long time ago, they always assume that the locations where the baby universes are born and die are 0 modes. And they even had like these powers of time like we had here. But yeah, most of what we did was trying to make this simple ID very concrete in JT gravity, and like just really derive that they are approximate 0 modes. But anyway, I think the main takeaway I want to give you for today is probably that there's just a very simple Lorencium picture that we can sort of imagine happens for generic black holes, and that explains this new type of universality that we're seeing. Yeah, that's basically what I'm saying here also. This sine kernel, like, I mean, it's really what people almost use as a definition of a quantum chaotic system. And so the same can be said of this round Plateau structure. And we've done like almost nothing. We've just Laplace transformed that guy and found this power series. So I would say this power series is just a time domain version of random matrix universality. So basically any black hole should play by those rules, should have a simple explanation, and we think that's this counting of the locations of baby universes. Okay, let's get to the details then. So first up, the Euclidean calculations. Now for the Euclidean calculations, what we can do is we can expand the spectral form factor into amplitudes which compute wormholes with geodesic boundaries with some fixed length. And this is like the trumpet amplitude of Sauchenker-Stanford. And in JT gravity, we call these Val-Petersen volumes. In general, they're just, volumes, but they have the same physical meaning. Like you just compute a gravity path integral with the boundary condition that the extrinsic curvature is 0 and the length is fixed to something we call B. Now, yeah, some very smart people have been able to show that, like, basically for any Delton gravity, this guy is some polynomial, a symmetric polynomial actually, in the squares of the lengths. Already, I think this is very non-intuitive from the gravity point of view, but nonetheless, it's something one can prove, and that is true. At any rate, so there are these polynomials with a maximum total degree of 3g. And this 3 is kind of important and also confusing for reasons I'll explain now. Namely, suppose now we compute these integrals. I mean, these are just exponential integrals of this type. We can all do that. This gives just a polynomial in beta plus it to the power d1 plus 1 minus a half from the prefactor. As we see here, these are from the two integrals. Now, let's just take t to infinity. And we see that very naively, but like almost obviously what this thing wants to give is a power t to the 3g because, well, precisely because of this degree of the polynomial. So, okay, what's going on? This Euclidean calculation wants to give 3 genus, not 2 genus. And I said this 2 genus is universal and should explain this plateau roughly. Now, what ends up saving the day is that basically for any dilaton theory, and I want to emphasize that it's kind of non-trivial, like it's not just something for JT or for one particular model. For any theory, you can compute these volumes. And what ends up happening is that the terms multiplying these odd powers of time for a large enough power add up to exactly 0. So it's not like any approximation or something, it's just a sum of numbers that's exactly 0 for any theory, and the sum does depend on the theory. But because of these sort of miraculous cancellations, we do recover in the end the claimed answer. And yeah, the rest of this Euclidean section is going to prove to you where these cancellations come from. Just to set your mind, here is the simplest example, which is a genus tree wormhole. And okay, you see here some numbers, and you can check for yourself that they add up to 0. And I can promise you, if you go to a higher genus, that this becomes absolutely horrible. And this is like a giant sum of numbers that seem totally uncorrelated, and yet the answer is always 0. So yeah, it kind of blows my mind, but it works like this.
Is there some systematic cohomology argument or something?
Yes, and that is going to be the gist a bit of that. So I want to give sort of an underlying mechanism and yeah.
When you say for finite beta, so that's before you even get to your part of the work?
Well, in this piece, I made an approximation. I put beta equals 0. Now, if I take this formula, I can Taylor expand it for small beta roughly, or large t, that's the same. So I get like terms with slightly lower powers of time, but with like powers of beta multiplying them. And those also give constraints.
So when you go to finite beta, you get weird cancellations like that at every order in beta?
Yes, precisely. So these guys will always be there, even at finite beta, but then as a Taylor series in beta, you get extra constraints. And okay.
Do these constraints, do they repeat somehow at some, or they're totally different at every order in beta?
Yeah. Yeah, they involve different coefficients. Or yeah. Well. Well, okay. Okay, so a generic mechanism for this sort of magic, for me at least, is what's next. So now a useful fact. Okay, the next 3 slides will be the most technical of the talk, but I'll try to give you a little bit of intuition for what's going on, and then if it's a bit hard to follow, then you can just tune out for 5 minutes and then afterwards pick back up. But I think it's very simple in the end. So a useful fact is that for any Delton gravity, the variance of the partition function can be computed as the sum of what people call intersection numbers, which are these guys. So I'll explain in a bit more detail now what this means and how you should think about it from a physical point of view rather than from a math point of view. So these, first from a kind of mathematical point of view, these tau k's, you should really just think of them as like some two-form that is defined on the moduli space of Riemann surfaces. And then these correlators, they're just integrals of two forms over moduli space. So not really anything magical going on there. These are like very explicit two forms that one can write up and compute an integral of in principle. Okay, it's not so easy as I'm portraying it right now to compute those integrals, but that is the basic idea, like nothing more than that. Oop. Okay, slide 16. But more intuitively and kind of in the same, well, still staying within the same spirit, I want you to think about this integral more like this. So it's still an integral over the moduli space, and I have some measure on the moduli space, which I wrote as e to the minus action, but that's maybe not too important. Just think of it as some measure on the moduli space, and then these taus as inserting basically some functions of the lengths of the boundaries, with the property that if I take this function of the length and I carry out this sum here, then I recover the trumpet. So what this ends up doing, if I compute this sum, is I'm integrating some trumpets, gluing them with the external lengths, the b1 dot dot bn. And then otherwise, the other part of the integral is just computing these volumes for me. So that is sort of the way these, if you remember the way how these multi-boundary amplitudes are computed in gravity, you have trumpets, and then you have these Wormhole amplitudes. And the Wormhole amplitudes are integrals over the moduli space of Riemann surfaces with some measure, which is, in very specific cases, simple, but usually extremely complicated. Okay, the rough idea now is that we can think of this exponential here that I'm defined, where this gamma case are defining different models of Delton gravity. Because this is an exponential, I think it's not too hard for you to imagine that this is like inserting kind of an action in this thing, or like changing the measure on moduli space. And that is indeed what happens. So different lambda k's or different theories correspond with different measures on the moduli space, or more in Delton gravity terms that maybe some of you are more commonly thinking about. This exponential of gamma k's is just going between Delton gravities with some different Delton potential, where there's some very explicit dependence of this potential on the gamma case. But all of this is kind of the same logic. Like if you take some operator and you put it in the exponential, okay, now you're changing the action, whichever way you're preferring to write this up. It's always like that. So, and in particular, JT, the way that it works for JT gravity, so for JT, the gamma case takes some very specific values. And the values are such that if I have this guy and now I insert this exponential, that actually the measure becomes just a flat measure on moduli space. So that's one of these cases where the measure becomes super simple. And now I adjust this flat measure, and I have the trumpets. And this integral over moduli space computes the Wald-Petersen volume, and I get the good old wormhole back. Okay, and the other theories were basically the same. All this to basically give you some intuition for this relation, what it means, and I hope this helped a bit. But now I want to proceed with our proof of where these powers come from. And for that, I'll introduce a new set of variables, y, which are functions of the gamma k. And I'm defining them as follows. So because I have an infinite set of gamma k's, I have an infinite set of y's, and I can make this map. So what I get here in the exponential now is sum over y, and sum over k, sum over y, and then sum over k, yi to the k tau k. So if I expand out this exponential, I get basically sums like this out in front again, with the sum over k playing the same role as the sum over d here. Like I get terms like yi to the k tau k, right? So if I expand out this guy, completely expand it out, I just get like more and more of these taus here and more of the y's in front, over which and then I'm summing over all their exponents. And I also have a sum over their indices, but the indices are not terribly important here. Yes.
Are you calling this as open close because these space-times look like wall sheet and an exponential is just attached to the brain, can be viewed as a background?
Yes, precisely. Yes, indeed. I will explain that a bit more on the next slide also. But yes. So as you see here on the right-hand side, what we have is precisely a multi-boundary connected correlator. And so if you remember, I defined the two-boundary connected correlator like this. Now I have n of these guys here. I'm computing the m-boundary connected correlator. But now there's no, since I have gotten rid of the exponential here, I'm basically reducing my calculations to a very specific theory where I've no exponential of these operators inserted. And this very simple theory is often called topological gravity, or the Airy model. And this has been studied to death by a lot of clever people. And in particular, Koncevic, Witten, and Okunkov have derived exact expressions for these guys. And for these guys in this simple topological gravity theory. And like a lot of interesting properties about these are known. And in particular, like recently this summer, there was a paper by Enard, Lewansky, and Ohms who proved a certain property of these intersection numbers that will suffice for us to prove this power expansion. So let's just get right to that after a small intermezzo. And the intermezzo is to explain your question a bit more. So I want to emphasize that we started with like a two-boundary observable, and now we have a many-boundary observable. And the mechanism at work here is really exactly open-close duality in string theory. If we view the gravitational path integral as a string theory, which for these models you can actually do, people call that minimal strings, then okay, you have an exponential of operators, and an exponential of operators is otherwise known as a D-brane. Because a D-brane is just, you have just this boundary condition, and you will let any number of strings end on that. And okay, we know boundary conditions and operators are basically the same thing. Yeah. Long story short, open string description, many boundaries, strings ending on D-branes. But we can also view that as the D-branes changing the closed string action, and then we have a slightly more complicated action, but we have no operators. Sometimes this is super useful, sometimes this is super useful, and in this case, this is super useful. Because now we can just compute everything in this theory and make generic statements about any action here. That's a bit the gist. And this is really nothing more than what the people have been are doing with this guess of defects, of course. So yeah, all credit to them. Okay, now very quickly, the argument for how we get our powers. And we introduce the following elementary symmetric polynomials following NR and company. Well, this whole slide is following NR and company. And then we can rewrite our multi-boundary correlators as functions of these polynomials, of the lengths. So here we had some lengths and then these so-called intersection numbers, which I told you just some integrals over moduli space. And now I just basically take linear combinations of them to rewrite them like this. And this guy will be like some complicated linear combination of these intersection numbers. Now, as I told you, Witten, Kontsevich, Okunkov know exactly what these guys are for this Baire or topological gravity or Airy model, whatever you want to call it. And what NR and Lebowski and Ohms observed is truly remarkable, namely that if you write these multi-boundary correlators using these elementary symmetric polynomials, then there's a lot less of these terms than you would think. And in particular, what they found is that a lot of these coefficients, which are very complicated linear combinations of intersection numbers, are actually vanish. And this is the general rule for when they vanish. Now, this plays right into our hand. Because if you remember the type of expansion that we had for the spectral form factor, start with a two-point function in any theory, decompose it into n-point functions in simple theory. But all these guys that kind of define the theory, they don't depend on time. Like time is a boundary condition in the theory, not what's defining my theory. So if I take t to be very large, these y's, they just remain numbers. And that means that all these elementary symmetric polynomials for late times will scale as t squared. Like at most I can have here, like say beta 1 is beta plus it, beta 2 is beta minus it, and the other guys are just boring numbers. Like at most I can always have the product of two of these betas. So I can never get something more than t squared. And that means that this product that appears in the expansion here can scale no faster than t to the 2 times the sum of the powers of E2 dot En. It's important here that E1 is the sum of all things and does not scale with t because I have plus it here and minus it here. Now if you see this coefficient, this should ring a bell. Because this is the same coefficient that appeared here. And okay, that means basically we're done. Like all terms in this expansion with powers that scale too large vanish. These people basically proved that, and we're just applying it in this situation. It's still a bit magic to me, but okay, they proved it, so it's fine. Okay, so that concludes the Euclidean part of our discussion. Now let's get to the Lorencium piece. Okay, this is getting a bit annoying. So just to summarize a bit, we've learned that the probability that a particle reappear near the boundary via a process involving g+1 wormholes, or g, whatever, grows universally as t to the 2g+1. And the sum converges to the plateau. And in turn, this is how gravity reveals the discrete nature of quantum black holes. But admittedly, as I also told you in the beginning, the methods here and these cancellations due to NR and company, kind of specific, I would say, or guess, to 2D gravity. And like more importantly, personally at least, I felt like this whole Euclidean calculation was like fighting an uphill battle. Like you start with something, and the first thing you do, you see, oh, t to the, like, naively, this thing just wants to scale like temperature to the 3g. Like it does not want this power to come out. And you have to like really struggle it and, I don't know, draw these powers t to the 2g+1 from the claws of the feet or something. And I don't know, it just didn't feel very intuitive. But so given the apparently sensitive Lorencian nature of this thing, like somehow magic happens when I replace beta by plus minus IT for some reason. Given this apparent sensitivity, one would think that there should be an intuitive and universal Lorencian explanation of these powers, which would apply hopefully beyond 2D. And so in the remainder of our talk, I'll present this proposal and then make it precise, or as precise as possible in JT. Okay, so here's the proposal. I already told this at the beginning, but maybe you've forgotten. And also I have a picture now. So in Lorentz signature, we want to think about space-time wormholes in the way that a child would. Namely, like the wormholes, they're just baby universes which can detach from some parent and then reattach to them at some later time in the future. And at the interaction times where these wormholes are made and die, there's some d-2 sphere on which the metric vanishes. Because it's like a sphere that has to shrink to a point for this to take place topologically. Which means that the metric is singular at these locations. Now, the spatial locations of the spheres, or in 2D, they're just, in 2D, the sphere becomes 2 points, as often. The spatial locations of these spheres and the times at which these interactions take place, those we want to think of as just moduli. And I think it seems natural to believe that they're approximate zero modes. And as I already told you, this was actually assumed in all of the original Baby Universe papers, so this is not, to me, a bold assumption. Then the argument is extremely simple. The boundary conditions tell us that we have an amount t of Lorentzian time at our disposal, and that means that the moduli of these wormholes should be integrated roughly from 0 to t, with some constraints on how we order them. Now, if we include the standard factor of t that Schenker-Sanford found for the double trumpet, which is like a rotation zero mode that is telling you the relative choice of left and right boundary times, then okay, we already recover our scaling t to the 2g plus 1. Okay, so it's obvious, it's easy, and I think that is what a candidate for universal physics should look like. Okay, so now the remainder of this talk, well on time, I will try to make this precise in JT. Okay. So it's well known, I'm not citing a lot of people here. I found out that even Horowitz was saying this in 1990, but it's well known that Lorentzian topology change requires a singular point in the space-time. As I told you earlier, points where the metric vanishes because the parent universe has to sort of touch itself for the baby universe to be able to detach. Now, the simplest argument, I think, in favor of the singularity we can give in JT gravity using the Gauss-Bonnet theorem, which is, okay, forget a bit about the boundaries for a sec. They end up not being important here. Gauss-Bonnet just reads as follows. So basically, square root g times r integrated over space-time gives minus 8 pi g. So in JT, unless we do something special, r is minus 2 everywhere. However, in Lorentz signature, square root g is imaginary or almost imaginary, and this guy will be imaginary, which is a contradiction because this guy is real. However, Luca Sorkin explained how to resolve this, namely the aforementioned singular points, which they call crotches for reasons that will become more obvious when I draw some diagrams later on. They have the following property, namely that square root g times r plus 2 is minus 4 pi times the delta function at the crotch. And now this is perfectly fine. Like square root g can be imaginary anywhere, everywhere. The 8 pi g is reproduced by the delta functions at fire. Like we have 2g locations where the baby universe dies and is born. Each of these gets a delta function, and summing over them, 2g times 4 pi, 8 pi g, which is correct. Okay, so this seems like a promising candidate, these Lucas-Sorkin geometries. So,
I'm sorry, Andreas, if you're going to be presenting on my work, you should be citing me.
It's coming, Michel. 100%. So, yeah, Michel also studied some of this stuff, but I'll tell that in more detail later. So to reproduce these powers of times, I think the question we want to answer right now is how can we build geometries like this in ADS? So can we find geometries on our double cone geometry that have this particular structure? And to do that, we will proceed as follows. So consider first the double cone in Rinder coordinates, which is the following metric. And okay, this is maybe a bit of an unusual way to draw the double cone, but what I've just done is usually people draw it like this. If anyone's watching on YouTube, you probably can't see this, so sorry. So this is the right wedge, and this is the left. What I've just done is like I've flapped this open, basically. And okay, the metric here, the boundary conditions have a plus I here and a minus I here. You can find it very nicely by introducing I epsilons in this piece also. Okay. So now to obtain geometries where square g times r plus 2 is minus 4 pi delta, we can make the following identifications on this sheet. Namely, I don't know if the colors are coming through. Not really, but okay. So what I did here was, or what we did here was you take a slice, you make a cut from here to here in the double cone, and another cut from here to here. Then you identify the blue slice with the blue slice, and the black slice with the black slice. And this you can do because the extrinsic curvature on these slices is the same. And because these slices also have the same lengths, which is what is required for getting smooth geometries. And the points here, those will end up having this delta singularity. So I think, yeah. Okay, let's proceed. Now, to appreciate that this is locally the same as the singularities of Lucas and Sorkin, the following visualization helps, where we separate the two wedges, like the left and the right wedge. Let's just imagine separating them here and turning the left wedge around. And now it looks like this. And now I think it's pretty easy to see for you. If I glue blue to blue and black to black, then this is a wormhole. Like I have just two sheets, and I have just a hole through them that I can peek through. I think this should also clarify why Lucas and Sorkin call them crotch geometries, because once I make this gluing, then like the bottom part of this diagram, this looks like the crotch of a pair of pants, but where I've cut open the pants along its seams. And in particular, you also see the 4 pi opening angle around the crotch. Namely, say I take a circle around this point. I go 2 pi here. Then I'll come out this way, and I'll go an extra 2 pi. So in total, I've traveled 4 pi. And then you can sort of follow the rules of, or just you can compute it by hand and see that that means that the curvature has the following prefactor for the singularity, which is precisely what we needed. Yeah, again, I want to emphasize that Lucas Sorkin did this a long time ago. The extra ingredient we have here is that we want to put them on ADS metrics, and that sort of constrains the locations of where these crotches can be. Okay. So now that we have our candidates for Lorencium wormholes, I think two more obvious questions remain. One is, well, this may not be an immediate confusion to you, but I'll first confuse you and then tell you how it's resolved, is how can these guys überhaupt contribute to the JT path integral? And then the second question, and that is where, at least to me, Michel's work was instrumental, is which configurations contribute and with which measure? And this is, of course, very important to get the right powers, because we can say whatever we want, but ultimately, as I told you in the beginning, the gist is to prove that these locations of where the baby universes are born and die are zero modes. So it's very important that they contribute with a flat measure, and also that they all contribute. But first, yeah, let's confuse you and then hopefully unconfuse you a little bit about the first question. So for that, we should remember that the dilaton field acts as a Lagrange multiplier in the JT gravity action. And if I do the path integral over phi, as people always do in JT gravity, they say, like, oh, okay, I integrate phi over all imaginary values. This is just a Lagrange multiplier generating a delta function. Now, this localizes on exactly square root g times r plus 2 is 0 everywhere. So, okay, naively, path integral does not pick up any of our single Lorencian crotch configurations. So we can say whatever we want that we want to count them, but the path integral is telling, no. However, well, I want to maybe confuse you extra, I want to point out that exactly the same situation occurs for the Lorencium black hole and explain how it's solved there. And this was discussed in a recent paper by Don Merolf. And maybe there have been other papers on the subject. I'm sorry if I'm missing them, but they will be cited in the upcoming paper then. So all these Lorencium black holes that contribute to this actually all have conical singularities at the horizon. Like, you can think of the geometries contributing to a truly Lorencium path integral as basically just 1/2 of the double cone. Like, we basically have just this triangle where we identify the top and the bottom by a Rindler boost. And then what ends up happening is that at this point you have some sort of a conical deficit. But this means that naively also the JT path integral for the black hole would be 0 in Lorentz signature, which is bad. But as Don Merolf explained, the way to proceed in that case is to first keep the dilaton at the horizon fixed, and only in the end integrate over this modulus. And this is a bit similar to this integral. Namely, as I told you, for the wormhole, what we do is we keep the length fixed, then you get a nice solution, and then you can do the integral in the end. And in that sense, it's similar here. Like, we keep the dilaton fixed at the horizon, and only in the end we integrate over that modulus. So very concretely, and this I think is highly inspired. I don't know if Don was inspired by that, but at least this is inspired by the constraint Instanton construction of wormholes that Douglas talked about in the appendix of his paper, and also Cutler and Jensen wrote a paper about. So very concretely, in JT gravity, we just insert the following delta function. So we fix the area at the horizon, and in the end we want to do the integral over the area. Now this delta function, for that we just introduce a Lagrange multiplier, and like funny enough, because we now put this in the exponential, the Lagrange multiplier includes actually a defect in the JT path integral. Then we can do the JT path integral with this defect inserted. Now the psi path integral does localize on an actual physical configuration. Okay, and then if you include the Schwarzschild fluctuations, integrate over alpha, first you end up recovering the correct black hole partition function in the following form. So if you, this guy you cannot really compute for purely Lorencian things, times, but for Euclidean times, you can do this integral and it reproduces the correct answer. I think this a squared is also what appeared in your talk last week for the ADM energy. Now it's still a bit unclear what goes wrong with the original Delton integral. But presumably it's some sort of contour deformation, like we start from the Euclidean path integral, but with Lorencium boundary conditions. And there we have only sort of complex metrics in the bulk, but mostly Euclidean metrics. And there we can sort of do the Delton path integral over imaginary values. But somehow when we go to these almost everywhere Lorencium metrics, in that contour deformation somehow we should also deform the dilaton contour and cannot just integrate psi from minus I infinity to plus I infinity everywhere. I don't know precisely yet how that contour deformation works, but at least it's reassuring that for the black hole it gives the correct answer. And truth be told, for the Lorencian case, it also gives the correct answer because we have this independent Euclidean calculation that I just presented. Okay, so this motivates us to apply the same techniques on the crutches. And what we will do is we keep the radial location of the crutches fixed, which is like keeping the area fixed, and only, or the entropy, whatever, and only in the end integrate over them. Okay, in this case, the alpha integral will only fire for the specific values that correspond to the 4 pi angle. Okay, now to the final part. With all the, groundwork or preparation work out of the way, we want to find out which configurations we should count and which measure. And for that, we'll build on some recent work by Misha, which I think is appearing soon. Now, the crux is to find a set of configurations which covers the moduli space of metrics modulo diffeos exactly once. Now, as you know, when smooth Euclidean metrics are involved, this is difficult. Typically, we work with Teichmüller coordinates, like length twist coordinates, and then the mapping class group is hard, and okay, we required Mirzakhani to solve this problem for us. However, there's another famous slice of moduli space of metrics, modulo diffeos, which is called Lycon gauge. I think originally invented by Mendelssohn. Apologies if I'm wrong. And Lycon gauge tells us to integrate instead over metrics with the following, which satisfy the following equation. So they're flat everywhere, except that they have some crutches at very specific locations. Now this plays right into our hand because they are related to the ADS crutch metrics that we were discussing just by some very simple transformation. The reason that this transformation is simple is basically because we have the same deltas appearing here and here. Whereas for those of you who might be familiar with the original Lycon construction, their goal was to start from Euclidean metrics without sources and go to Euclidean metrics that are flat with sources. We want to go between Lorencium metrics with sources to other Lorencium metrics with sources. And that ends up meaning that this guy is not sourced and it's just a simple smooth function. Okay, so the usual light cone diagrams for closed strings, they look like this. And the moduli space and measure on them is worked out by Giddings, Doker, and Fang. Long story short, the moduli involve the crotch times Ti and Tf, and then like the lengths of the closed strings and some twists. And then the measure, crucially, is flat, modulo some ratio of determinants, which is as follows. Now, though I won't present the details here, we found a way to map these closed string moduli to open string moduli by cutting open the open strings as suggested or basically as instructed by Giddings, Doker, and Fang. And in doing this, we could derive which of our crotches on the double cone contribute to the JT pattern integral, basically all of them, and also with which measure. The important point is that from this analysis, we find that indeed the interaction times do behave as approximate zero modes. And an important part of that calculation is to prove that these ratio of determinants does not depend on time for large times, which you can do, but again, I will spare you the details. Now, in the end, though we had to take some detours, I think we were able to prove that in JT gravity, indeed from this Lorencium perspective, you find that this genus G amplitude has this scaling t to the 2g plus 1 that we expect on general intuition about Lorentzian spacetimes, that we found from the Euclidean calculation, that we found from the boundary perspective. We now also reproduced it from a Lorencian perspective. And that's basically all. Thank you.
Questions, Andreas?
I have a basic question. I lost track of something in all the calculations. How does the scaling of t to the 2g plus 1 for the connected partition function lead to the plateau?
Well, perhaps I would say it's maybe a bit of a stretch to say directly that the scaling leads to the plateau. It's just that in all cases, the plateau follows from a series with the scaling. So it's a necessary condition. Like the series that converges to the plateau has the scaling. But to actually find it, you also need the prefactors.
Right, okay.
It's yeah. It seems a universal ingredient, but then to actually get the prefactors, well, for now, I can only say that you need more specifics of the theory.
Any more questions? If not, thanks, Andreas, again.